I am going to be talking about how we can use a network of very precisely timed radio pulsars to detect low-frequency gravitational waves, most likely emitted by supermassive binary black holes at the cores of merging galaxies. And this work is in collaboration with NANOGrav. We're about 150 students and scientists, mostly students actually, at about 50 institutions. Most of these institutions are small colleges with just one faculty and a few students. We've been at NSF Physics Frontier Center since 2015. We'd love to see you at our meetings. We always welcome new members, so if you're interested in what I'm talking about, send me an email and come to one of our meetings. So I'm going to start with just the super big picture of galaxy evolution. The question that we set out to ask with our NANOGrav experiment is, how did galaxies evolve through cosmic time? So if we look back at galaxies that were formed a really long time ago, the very first galaxies, they're really small, and they're very irregularly shaped. If we look at galaxies formed more recently, they're much larger, and they're much more structured, like our Milky Way galaxy. And the theory is that this evolution has happened through mergers. So smaller galaxies merging to form bigger and bigger galaxies. Okay, so this is a really nice picture. We can see lots of evidence for this. So this picture here, whoops, I didn't mean to do that. I'm giving up my, there we go. Okay, so this picture here, you can clearly see that these two galaxies are in the process of merging. We can study them electromagnetically, that's great. However, there are a lot of really interesting questions about the very final stages of a galaxy merger. When the galaxy may look like this, electromagnetically, with light, you may have no idea that this galaxy was the product of a merger. And the only way to tell is if we could resolve the two black holes that were at the cores of these galaxies and are right now on their very last kind of dance with death. They're going to that final merger. So how are we going to do it? How can we study these black holes at the core of this galaxy? Some of the questions we want to answer, by the way, are really important, right? So how long does it take these black holes to merge? Are there processes that will speed it up? Are there processes that will stall it? What's the astrophysics happening in these final stages? And this is something called the final parsec problem, or the last parsec problem. And of course, we can do this not through light, but with gravitational waves. So gravitational waves are a prediction of general relativity. They're produced by accelerating massive objects. So these black holes, as they orbit each other, will lose energy to gravitational waves. Their orbit will get tighter and tighter and tighter. Eventually, they will merge into a single black hole. And these gravitational waves are ripples in space-time, so they stretch and squeeze space-time. They have, of course, been detected by LIGO. So LIGO is sensitive to gravitational waves from what we call stellar mass compact objects, so neutron stars and black holes with masses of, say, a few to 100 times the mass of the sun. LIGO's detected gravitational wave mergers from about 70 or so of these events so far. The first one was in 2016. And if you look at the waveforms of these gravitational waves, you can see that the frequencies that LIGO is sensitive to range from about 10 hertz or so up to sort of hundreds of hertz. Okay, so these are very high frequency waves. These events happen well within the time span of a second. Okay? So this is LIGO. That is all really great and really exciting. To segue to our project, let's first just look at how LIGO works. Okay. So LIGO is an interferometer. What that means is that it has two vacuum tubes with lasers that run along these tubes. These vacuum tubes are at an angle of 90 degrees to each other. And when a gravitational wave passes through this interferometer, it stretches one arm and squeezes the other arm because of the quadrupolar nature of gravitational wave perturbation. So one arm gets a little bit longer, one arm gets a little bit shorter, and this difference in light travel time along the arms is detected as an interference pattern at this interferometer. Okay? So that's LIGO. So LIGO has arms that are about 4 kilometers long. The test masses at the ends of those arms are about 40 kilograms. Okay? And it's sensitive to black holes and neutron stars with masses 10 times the mass of the sun or so. How do we build a detector to detect black holes with masses 1 billion times the mass of the sun? That's what we want to do, right? Because these black holes at the cores of these merging galaxies are very, very massive. Well, we need to build a much, much bigger detector. And so that's what our project has done. We've built a galactic scale detector using a network of radio pulsars. And so radio pulsars are rapidly rotating neutron stars. They are born in supernova explosions. As they rotate, there we go, their spin axis and their magnetic axis are misaligned. And so as they rotate, they act kind of like cosmic lighthouses. So for every rotation, we detect a radio pulse. Okay? So these are nature's celestial clocks. They're extremely accurate rotators, and we can measure the arrival times of these pulses to very, very high precision with large radio telescopes. And that means we can look for any small perturbations to those arrival times due to astrophysical effects like gravitational waves. Okay, so our experiment is a pulsar timing array experiment. We can't do this experiment with just one pulsar. If we saw a little perturbation in just one pulsar, no one would believe us if we said that's a gravitational wave. What we need to do is look for a correlated signature that has this very special quadrupolar correlation predicted by general relativity in the data from an array of pulsars. A little bit of details about how we do this analysis. So, these perturbations, there's going to be a perturbation at the pulsar, right, the effect of the gravitational wave at the time the pulse was emitted. We call that the pulsar term. There's another perturbation at the Earth at the time we detect that pulse. And the Earth and the pulsar, you can think of them as both bobbing around in this sea of gravitational waves. Using this experiment, we can detect a couple different kinds of sources. So we're sensitive to a stochastic background of gravitational waves. And that just means the superposition of all the gravitational waves in the universe. And we can also look for individual sources of gravitational waves. So gravitational waves, for instance, from like an individual black hole binary. So we have constructed a detector made of about 70 pulsars, very rapidly spinning millisecond pulsars. Pulsars are quite faint, so we need the largest radio telescopes in the world to do this experiment. Right now, our main telescopes are the Green Bank Telescope in West Virginia, and the Chime Telescope in British Columbia in Canada. We observe pulsars over a range of radio frequencies, anywhere from daily with Chime to once every month with the Green Bank Telescope. We have small programs at the Very Large Array and with the FAST Telescope in China also. The Arecibo Observatory in Puerto Rico was our cornerstone. It had the largest collecting area. We had much more time on it than the Green Bank Telescope. So our program really took a serious hit when this telescope collapsed at the end of 2020. We've been lucky to get some funding from the Moore Foundation and from NSF to up our usage on the Green Bank Telescope. We still haven't nearly replaced the sensitivity that we've lost with Arecibo. So this is something that we really need to try to address over the next decade. So we're a pulsar timing experiment, and this little graphic illustrates what it is that we're doing. So every time we observe a pulsar at that epoch, we take the data that we take, on that pulsar, something like a half an hour of data, and we fold the data, which means we add up every pulse on top of every other pulse to get a very high signal-to-noise pulse profile. So this is our pulse profile here that we get over one observation. And then we measure the time of arrival of this pulse at our telescope as accurately as possible. And we can do that to sub-microsecond, sometimes 100 nanosecond precision. And then we make a model. And this model accounts for all the astrophysical stuff that we know is happening that's going to affect the time of arrival of that pulse. We call this a timing model. And then we use that model to predict when the next pulse will arrive, when a pulse a week later, a month later will arrive. We take another observation of that pulsar here. We measure the arrival time here. And then we subtract the arrival time of that pulse from the time the model predicted that pulse should arrive. And that is our timing residual. And if our model is perfect, all of these residuals will be 0 if we're modeling things absolutely correctly. And this is an example of one of these pulsar timing models. You can see that we have to account for a lot of stuff. We have astrometric parameters like where the pulsar is located, its proper motion, its parallax, of course, its spin frequency, its frequency derivative. These are parameters related to travel through the interstellar medium. This particular pulsar is in a binary with a white dwarf star, and so we have to also account for this binary motion, because that's going to Doppler shift the arrival times of the pulses from this pulsar. And these are some of the most precisely measured astrophysical quantities you will ever see. And I'm still flabbergasted when I look at these numbers. So we can measure the spin frequency of this pulsar that's 218.8118404171579 hertz. And we really do know that down to that very last significant digit. This pulsar is in a binary period with an orbital period of 67.825131000 days. Okay, so this is really amazing, and it's the huge timing stability of these pulsars that allow us to do this experiment and measure these things so precisely. So NANOGrav releases data to the community like every few years. We release these models. We release times of arrival. We release pulse profiles, which look something like this. And we keep growing the number of pulsars in these releases. So the release we're working on right now will have 67 pulsars. Our last one had 47 pulsars. So we're increasing the time span of the experiment, and we're adding pulsars, which continually increases our sensitivity to gravitational waves and all sorts of other stuff. And all our data is publicly available if you want to go and grab it. And just talking about this like bang for the buck concept a little bit, there's so much synergistic science that comes out of this that's not related to gravitational waves. Our pulsars are free. We don't need to pay for these detectors, and radio telescopes are a lot cheaper to build than LIGO. So this is a really good sort of like bang for the buck experiment. Okay, so because we're analyzing data over very long time scales, so like decades, right? We're currently looking at our 15-year data set. We're sensitive to very long period gravitational waves. So much lower frequency gravitational waves, way down here in the gravitational wave frequency spectrum than LIGO and like this planned space detector, LISA. Our strain sensitivity is roughly equal to the time, the timing precision of our data, which is, a couple hundred nanoseconds over the time span of our experiment. So this means we're sensitive to changes in path length to our pulsars of like 1 part in 10 to the 15. This isn't as good as LIGO. LIGO's down here at like 1 part in 10 to the 22 or something, but fortunately these supermassive black hole binaries are really bright gravitational wave sources, so there's lots of stuff for us to detect. Okay, so these are the data that we analyze. These are examples of just 3 residual plots for 3 different pulsars. So this is time here, and these are the residuals that we measure. You can see they're mostly consistent with 0. So our models are doing a pretty good job, but you can also see some of them aren't. There's some unmodeled noise in this data. The different colors are just different radio frequencies. And if there's a gravitational wave in this data, and let's say one from the stochastic background, from the superposition of all the gravitational wave sources in the universe, it will appear as what we call red noise in the residuals. So for any particular pulsar, this gravitational wave will just look like kind of like a slow, kind of quasi-periodic wander in the residuals. So it may not be apparent. It most certainly won't be apparent in the data from just one pulsar. We're only going to see it when we cross-correlate these residuals from all these different pulsars and search for this very specific angular correlation that we expect due to gravitational waves. And this is what that should look like. This is something called the Hellings and Downs correlation, because it was published by Hellings and Downs back in 1983. And this shows the correlation in these residuals we expect versus the angular separation between pulsars. And you see this quadrupolar nature of gravitational waves here. So if 2 pulsars are in the same direction in the sky, if they have an angular separation of 0, the residuals should be correlated. At 90 degrees, we should see an anti-correlation. We should see a correlation again at 180. This assumes that general relativity is correct and that we have an isotropic stochastic gravitational wave background. But this is very easy to derive. There's kind of no ambiguity that we should see this correlation in our data if there is a stochastic background of gravitational waves. The maximum correlation, you'll notice, is only 1/2. And that's because everything happening at the pulsars is totally uncorrelated. They're all at different distances. These gravitational waves are hitting them at different times. So the cool part is when we detect these gravitational waves, what we're actually detecting is the effect of the gravitational waves on the Earth itself, not on the pulsars. But that's why we don't have a perfect correlation, because these pulsar terms are just noise for the stochastic background. Okay, so in 2018, we had a pretty exciting time. So what we do is we do this correlation analysis, and then we calculate plots like this, which show the probability density of a particular amplitude, right? And I don't want to call this gravitational wave amplitude yet. This is just the amplitude of this common red noise in the data. And we at first calculated curves that looked like this, like these dotted lines here. And what you'll see is they peak at a particular amplitude. So I think it was this blue line we had originally, and we were really excited. We started popping out the champagne. This is great. We've made a detection of this noise in our data. And then we said, wait a minute, let's try to make it go away. Can we make it go away? And we could make it go away. And we can make it go away by using a different version of the solar system ephemeриds that we get from the Jet Propulsion Laboratory, which we need to correct the times of arrival of our radio pulses on Earth to the solar system barycenter. We got different answers depending which version of the ephemeris we used, and we realized these ephemerides weren't accurate enough for our purposes. We needed more accurate ephemerides. We developed a new code that fit for a better ephemeris in the process of doing our timing model fit, and then we got these solid lines, and these look like upper limits. So there wasn't a detection in 2018. This is an upper limit on the gravitational wave background, and we will not have this problem again, thanks to Juno, this spacecraft orbiting Jupiter. It turns out Jupiter was solely responsible for the problem with these ephemerides. We did not know the mass of Jupiter well enough, but this is going to be fixed going forward. Okay, so that was fun. And even though we just had an upper limit, we could actually do a lot of astrophysics. We could rule out models for black hole to galaxy mass. So there's a bunch of different models that predict what the mass of a black hole should be versus the galactic bulge. And when we could say some of these models are really disfavored, or else we would have already made a detection. So we're that sensitive that we're ruling out some models for black hole to galaxy mass. So that was cool. So now in 2020, our most recent data set, we did a similar analysis, and we calculated the probability density of a particular amplitude of common red noise, we'll call it for now, in our data. And we, again, get these really nice peaks, right? Very significant detection of a common red process in all the pulsars, that it's correlated among all the pulsars. This is super exciting. We get it whether we used a fixed solar system ephemeris or whether we fit for a solar system ephemeris. So there is something in our data, and we cannot make it go away. A common red process among all of the pulsars, really exciting. However, you'll see from this right plot, this is not so exciting. We do not yet see the very special quadrupolar signature that we expect to see in the pulsar timing residuals. The black points are our data. The blue dotted line is this fitted Hellings and Downs curve. So far, we do not see that correlation. This is exactly what we expect, though, for the first stages of detection, right? We expect to see this common process first and then later be able to resolve the spatial correlation. So this is OK, right? We are probably on the brink, but we can't say for sure that these are gravitational waves yet. OK, now this is consistent with a population of supermassive black hole binaries. We can look at the spectrum of this common red noise. And this shows the power, these gray bands here are the power at different gravitational wave frequencies. It's a very red process, lots of power at low frequencies. This orange line is our best fit. We can calculate the spectral index, which is shown here. So these are contour plots showing our spectral index. It's very steep. This is consistent with what we expect for supermassive black hole binaries. We expect a spectral index of around 4.3. This is consistent-ish with it. However, just to keep things exciting, fun, it is also consistent with what we expect for other gravitational wave sources, such as primordial gravitational waves, which Phil talked about, or even cosmic strings. And for those, we also expect red spectra with parallel indices in this same general range. So right now, we can't claim a source for these gravitational waves. We can't even say for sure they are gravitational waves yet, but it's very, very tantalizing. My bet is still in the supermassive black hole binaries because these other sources are predicted to have lower amplitudes, but we shall see. OK, so I only have less than a minute, so let me just wrap up with what y'all want to know. When are we actually going to be able to say whether these are gravitational waves or not? And of course, we've done simulations to predict this. In our current data set that we're working on right now, we call it our 15-year data set. It has 15 years of data. It'll be published within the next year. If what we're seeing now is indeed gravitational waves, we should detect these angular correlations with a signal to noise of like 4 to 7. This is a simulated plot, but it should look something like this. So this is really super exciting. So we could, within the next year, know whether these are gravitational waves or not. We will likely not be able to identify the source of the background. We won't be able to constrain the spectrum well enough to say, in a year, whether it's supermassive black hole binaries or primordial cosmic strings. The signal to noise will be even higher in combined data. We're working with our international colleagues to combine our data from our radio telescopes with their data from all of their radio telescopes as well. OK, and so finally, just a little bit about the future. One of our big goals over the next few years is to add more pulsars to the array. Our sensitivity is linearly proportional to the number of pulsars that we are timing. So the more pulsars that we can add, the better we're going to do. We have high school students throughout the United States in a program like helping us find new pulsars. We have one of them over here, Gurmahar. He's a student who was in our program, so you can talk to him about it and how great it is. If you know any high school students who want to help us, let me know. We also really need more telescopes. We need larger collecting areas and dedicated telescopes. We're super excited about the DSA 2000. This is a telescope that is in kind of the deep design phase. It's funded by Schmidt Futures. We expect to get a significant amount of time on this telescope. This will really increase our sensitivity. And over the next decade, of course, what we want to do is do astrophysics, right? We don't want to just say, we detected this. We want to measure its amplitude. We want to measure its spectrum. This will tell us a lot about how galaxies have grown and evolved over cosmic time. And within about 5 years or so, we'll be able to tell whether there might be multiple contributions to that background, right? Most likely, it's from a few different things. These supermassive black hole binaries plus a primordial contribution or something else. We'll be able to do that over the next 5 or 10 years. And then the next step, and we also expect this to happen over, say, a 5-year time scale, is detecting single sources, so single supermassive black hole binaries that we can observe both with gravitational waves and electromagnetically. So really opening up a new field of multi-messenger low-frequency gravitational wave astrophysics. So thank you very much.